So I want to talk about section 9.3, infinite series, the subtopic of writing a repeating decimal as a geometric series, and then expressing its value, its total, as a fraction or a rational number. So I want you to remember that every rational number, that's a ratio of integers, so any number like 1/5 or -2/3, these can all be written as either a decimal that's finite, so for example 1/5 becomes 0.2 and you're done, no more. Or -2/3, which becomes -0.666666 with a repeating, so that's a repeating decimal. So you either get a finite decimal or a repeating decimal, and that's for rational numbers. So then we know that we have also irrational numbers, and that's numbers like pi and e and √2 that cannot be written as a finite decimal or a repeating decimal. So a repeating decimal can be written as a geometric series, so I want to look at a particular example. So if I have the repeating decimal that has 0.027 as the repeating part, so it's 027, 027, 027, and so on. Another way of thinking about that number is 0.027, so just the first digits, plus then put zeros for those digits you already accounted for, and then the next 0.027, and then zeros for the first digits you already have, and then plus 0.27, and so on. And you see that that is going to be the same number if you add those all together. So do you see the pattern that if we write these as fractions, I'm going to have 27 over 1,000, which 1,000 is 10 cubed, right? Then I have plus 27 over 10 to the 6th, 27 over 10 to the 9th, 27 over 10 to the 12th. So hopefully you're seeing that there's a pattern that is forming. Now if you get the same number by doing the ratio of the fourth term to the third term, and the third to the second, and the second to the first, then that number that you get is that common ratio R for the geometric series. So let's look at what happens if you form those ratios for this series. Like if you do 27 over 10 to the 12 over 27 over 10 to the 9, then that's 10 to the 9 over 27 multiplied, right? Since I'm dividing by a fraction. So I get 10 to the 9 over 10 to the 12, which is 1 over 1,000. And you'll see if you do more of the ratios, you keep getting 1 over 1,000. So you're multiplying each term by 1 over 1,000 to get the next term. So that tells us that R is 1 over 1,000. And you can either do this in decimals or fractions, but the end we want a fraction answer, so you may as well work in fractions. So we have a formula from this section that says if the absolute value of R is smaller than 1, then your geometric series converges. So clearly this R is much smaller than 1. So in fact, this geometric series converges to A, which is the first term, over 1 minus R, the common ratio. So A is our first term. So our first term is 27 over 1,000 over 1 minus R is 1 over 1,000. So I'm going to have 27 over 1,000 over 999 over 1,000. So instead of dividing by the fraction, we're going to multiply by the reciprocal and see that the thousands cancel out, and you get 27 over 999. So this is the fraction that is exactly the same number as that repeating decimal. If you try it in a calculator, you'll see that they match up. So that's pretty amazing that you can write an endless repeating decimal as a fraction. So let's try another example. And in this example, you have some parts at the beginning that are not repeating. So I'm going to suggest that you write this as 5.12, then plus 0.0083, and then plus 0.000083, and so on. So I'm going to just keep this 5.12 part over here at the edge and add it back on at the end of the problem. So here I have 83, 10, 100, 1,000, 10,000, 83 over 10,000. And then I have plus 83 over 10, 100, 1,000, 10,000, 100,000, a million. So this is 10 to the 4, this is 10 to the 6, and so on, and you'll get 10 to the 8. So hopefully you're seeing that your R is 1 over 100 in this case. So your sum of your A R to the K is going to be A over 1 minus R, where A is the first term, so 83 over 10,000 over 1 minus, and your R is 1 over 100. So you're going to have 83 over 10,000 over 99 over 100. And to divide by that fraction, we're going to multiply by the reciprocal of 100 over 99. So then I'm going to have, let's see, if I divide 10,000 by 100, I'm left with 100. So I'm going to have 83 over 9,900. So that is for this decimal part. But now I need to add the 5.12. So that's 5 plus 12 hundredths, right? So if I want to write that as 99 hundredths, I'm going to have to multiply by 9,900 over 9,900. So when I do that, which I did, and now I'm not seeing the numbers. Oh, here they are. I get 49,500 plus 1188 over 9,900. So then my final answer is going to be 49,500 plus 1188 plus 83 over 9,900. So the number I get as my final answer, I don't have here. So let's see, 8 and 3 is 11, 9 and 8 is 17, 5, 6, 7. I'm getting 49,771, but check that over 9,900. And if you divide this on a calculator, you should get the exact same decimal number that you started with. So have fun playing with these. They're not likely to show up on a test, but it is a really interesting procedure and could be useful later. That's all.